Okay, so how's it going? Do I have any logistical announcements? I don't know. I didn't. I said something about a video for Friday, but I just X'd that out of the assignments page because I didn't have time to make one. So I'll just lecture on Friday. So no video for Friday, but I do need to post the Friday problem set, which I will do like ASAP after class, so you can get to work on it. I guess it'll be on dot product stuff. So, okay, how was that video? It was fine. Did you see my comment below the video that I forgot the most obvious way to determine two lines, which was like 2 points determine a line? I jumped right to the formulas like point slope and slope intercept. And so, and I hope that the idea of the normal vector was sort of interesting. You know, that like the most general possible line. Let's call this lines and planes. We're going to get into tangent planes very soon, and so we're going to really want to talk about planes carefully. But you know, the video sort of we got down to the idea that the most general equation for a line is this like a times x minus x naught plus b times y minus y naught equals 0, and x naught comma y naught is a point on the line, and a comma b, or ai plus bj, is a vector perpendicular to the line, which we use this word normal. It is kind of silly that there's like 3 different words for perpendicular in math: perpendicular, orthogonal, and normal. They all basically mean perpendicular. There are slightly different settings. There's slightly different places where you use those words. Sometimes you can be a little more precise about which word applies to which situation, but I don't know. They're pretty much interchangeable in this course. Normal slash perpendicular. To the line. Okay, so okay, so that was our sort of most general line thing, and the point I was making, right, was that the slope formulas are very discriminatory towards against vertical lines, and that makes me sad. Vertical lines deserve a place in our society also. Okay, so let's move to planes. Unless there are follow-up questions people had from the video, I'm happy to. Anybody found a point in the video confusing, or wanted further explication, or anything about lines? Okay, so let's do the same kind of discussion about for planes as we did for lines, which is what information determines a specific plane in 3-dimensional space. So what information determines, and I guess this is kind of mathematical lingo, determines a plane. It just means picks out of all the possible planes that exist in space. You know, here's a plane. So all the possible planes that we could have that exist in space, what information picks out a specific, what information do you need to pick out a specific one? What's the analog of 2 points determining a line? How many points do you need for a plane? 3, right? You need 3 points for a plane. Because 1 point, okay, there's a lot of planes to this point. 2 points, well, I can still tilt it this way. And then the 3rd point fixes it, right? So good, so 3 points. Maybe I'll call that 0 again. I don't really have a numbering scheme in mind, but it's sort of the most. 3 points I don't know why I need to number these. Let me just bullet point them. Or what else? What other information could determine a specific plane? Yeah, well, two vectors. So if I pick two directions, that certainly determines something. Does it determine one specific plane? If all the vectors were, or Iman, did you say something? You need a starting point also, right? Because we're talking about vectors as displacement. So like if I had two vectors, that could determine sort of two directions, like one vector here, and then another vector here, but then I could do this. And those would be different planes with the same two vectors, right? Trying to move this up and down in a parallel way instead of like this. Yeah, so a point and two vectors, yeah. That's what you're gonna say, like a point and two vectors. Yeah, so, or 1 point and two vectors sort of parallel to the plane. I guess I should say two vectors like along the plane, and also I guess not parallel to each other. Two non-parallel vectors sort of along the plane or in the plane or something. Maybe it's worth drawing a picture of a plane over here. That's a plane. Maybe I'll draw a few. Supposed to be parallel lines. Oh my God, that makes it look less like a plane, doesn't it? All right, it's supposed to be a plane. But so if I pick 3 points, right, that would determine a plane. Or you could think, do you see that these two pieces of information are kind of equivalent to each other? Right? Because if I pick one of these points and draw the vector to the other 2 points, that would be a point and two vectors. What else? If one vector could determine a plane? Yeah, a normal vector. If I pick a point in the plane, and then, so a point, so it has to go through this point, but then I pick a normal vector that actually is going to fix a specific plane, right? So that's good. And actually that's how we're going to write, that's how we're going to get the equation of planes is this way. So I should say, or 1 point. I guess I should have made this clear that this is in the plane. I guess that's maybe goes without saying. And a normal vector. Yeah, so that's nice. Of course, it's going to be harder to draw here, but I guess if I use like, if I say that's right angle, maybe that's a right angle. You see my little thing. So that's normal vector n. Okay. Okay, so that also determines a plane. And the easiest way to get an equation for the plane is to use this third one. So if we have this information, we can write down the equation of the plane pretty easily. Because let's think about, let me label these a little bit. So let's call this vector a comma b comma c. It's very analogous to that, right? Let's call this point x naught comma y naught comma z naught. And let's just say this is some other point x, y, z that's in the plane. So forget about this other point here for a minute. Let's just think about. And so this, I mean like a variable, like, sort of fixing this point and fixing this vector, and then this can move around. And this could be any point in space, but I want to specifically figure out a way to identify points that lie in the plane, right, to like satisfy the whatever the plane equation should be. And so how's that going to work? And maybe you read this section of the book too, but we do have this vector right here, right? How could I write this vector down in terms of stuff I've written on the board? Right, so that's going to be where we're going with this, which is like, yeah, we want these two vectors to be perpendicular, so the dot product should be 0. But in particular, just how do I write down this orange vector? Yeah. Well, it's going to be an equation for the, you guys are all jumping ahead of me, which is that you're giving me the answer already, which is going to be an analog of that. It's going to be an exact analog of that equation, right? But to see how this works, it's like, okay, there's a vector here, right? How do we write on a vector between 2 points? Exactly, right? So there's this vector. And it's kind of funny, I think I said this in the video even, that like a lot of times people will write this down this way, like a variable vector x stands for just x comma y comma z, or just in general, like if you want a variable for a vector. So that's x minus x naught, y minus y naught, z minus z naught. Okay. And so if you think about it, the point x, y, z is in the plane if and only if those two vectors are perpendicular. Right, so let me write that down. X comma y comma z is in plane, I guess, determined by, I could also say this plane is not determined by like n and x naught, right? In the sense that like x naught represents this point. I mean, it's a vector, but it represents this point and represents that vector. Yeah. That's a concrete point, but it's a variable point, so it can move around. Not sure what concrete, if that means not concrete or.
That is an exact location, or if that's just the variables.
That's just the variables, yeah. Like, so I'm fixing this point and this vector. And I'm saying that we could just take any point in space and make the vector x minus x naught, the vector from this point to that point in space. But that point will lie on the plane if only if that vector is perpendicular to n. Right, if it's not perpendicular to n, it will lie somewhere off the plane. I mean, if you want, you can think of this tabletop as the plane, and so the normal vector sticking straight up. And x naught, y naught, z naught's like in this tabletop. If I pick a point off the tabletop and make the vector, that's not going to be perpendicular to the normal vector, right? But if I pick x comma y comma z in this tabletop, then that vector is perpendicular to that vector. Okay, so this is in the plane if and only if, mathematician's favorite phrase, x minus x naught is perpendicular to n. Or you can write this as a vector equation with the dot product now, right? We know dot products are 0. That's how we determine perpendicularity. So this is kind of like the vector form. It's sort of nice to be able to write down some abstract type things like this. But if we write this out, this is like A comma B comma C dotted x minus x naught, y minus y naught, z minus z naught, 0. So this symbol also means if and only if. This double-headed, double-bodied arrow. So if you actually write this out, you get A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Okay. So this is sort of our general equation for a plane. For example, if we just had like, just some simple examples just to do a sanity check on this to make sure it makes sense to us. If we had like a horizontal, so example, I don't know, a horizontal plane through a point like 0, 0, 2 or something. Right, what's the equation of that plane? Without even thinking about that, just what are all the points in that plane satisfy? Z equals 2, right? I.e. equals 2. The normal vector here is what? What's the normal vector to a horizontal plane? K, or any multiple of K. I mean, it could be 7K or negative 3K or whatever, but it doesn't really matter. Might as well just pick K. So that's 0, 0, 1. The angle bracket notation. And so the equation from here, just to check that it matches what we expect, it's 0 times x minus, actually, maybe I'll do something like this. Maybe I'll put like 1, 3, 2, because it didn't matter what x, y, and z were, right? I mean, x and y were, as long as z is 2. So 0 times x minus 1 plus 0 times y minus 3 plus 1 times z minus 2 equals 0. And is that the same thing as z equals 2? The zeros here, these terms just go away. And so that's the same. That simplifies. It simplifies to that. Right. Okay, so that's just a quick sanity check. In general, it's just nice that this works this way, like somehow, like if you want to write down some plane tilted at a certain angle, if you can sort of figure out the normal vector, you can just write it in a point, you can just write it down immediately. Now, the real question though is, what if I gave you 3 points? How would you determine, like it should be if I gave you 3 specific points in space and we're gonna do this, after we do this abstractly, I'm gonna actually have you guys pick 3 points and we're gonna find the equation of the plane. Just pick 3 random points and find the equation of the plane. Yeah, so if we have 3 points, we can make 2 vectors. And then how do you find a vector perpendicular to both of them? Cross product, right? So there's a cross product thing here. There's a couple ways to do it, but cross product is one of them. I mean, cross product's a good one. We've just learned the cross product, we might as well. So note, given 3 points, say we want to find the equation of the plane containing them. So the 3 points gives us 2 vectors, right? We can make 2 vectors just by subtracting, picking any 2 of the pairs and subtracting the coordinates. And let's just call those like V1 and V2 that are in the plane, quote unquote, in the plane, or along the plane. And then compute N is V1 cross V2, right? So you can actually compute the cross product of V1 and V2, and that is definitely perpendicular. Since it's perpendicular to both V1 and V2, it's perpendicular to the whole plane, right? And then if X naught, and then we can write down the equation. I'll just say, you can just pick any one of the points that we started with and use that as our point. And since we have a normal vector and a point, and a normal vector, and normal vector. Okay, so yeah, N is perpendicular to V1, and is perpendicular to V2. So N is perpendicular to everything. Does that make sense as a process? Like, what's kind of funny is that if you pick any of the 3 points that you started with, you should, as your point, as your like X naught, as your X naught, Y naught, Z naught up there. One thing you could do is once you have it in this form, just pull this board back down for a second. You could sort of distribute this out and write it all back down as like AX plus BY plus CZ equals D. If I multiply through all the A's and move all the constant terms over to the other side, you can write it in that form, which is sort of nice. And so it's surprising a little bit that it doesn't matter what point you use, you should still get the same D over here, like which of the 3 points, which is a little not obvious, but let's see it actually, because what I want to do now, any questions about anything I've said? Questions are good. I feel like I'm just chugging along here. Yeah, Caleb.
So the way that we just computed that plane is independent of the way that we initially did it with this equation. So we're different than that.
Well, we're going to use that equation, but we just need to figure out what A, B, C are. And this calculating N tells us what A, B, and C are. And then picking the specific X naught, Y naught, Z naught is picking one of the 3 points. And I guess I'm claiming it shouldn't matter which of the 3 points you pick. Yeah. Sure. The equation of a plane. I think in this section, when I start assigning problems about this, there will be things like write down the plane through this point parallel to this other plane. But if you have the equation of the other plane, then you can write down the normal vector. I mean, that's the other thing that's nice. If you have an equation of a plane in this form, you can write down the normal vector immediately. It's just the coefficients, A, B, C. Right. So sometimes, and the book asks a bunch of questions like that, which I'll assign, some of which I'll assign. So yeah, so but there's always, you can always recover either like some other normal vector or, whatever. Anything else? Okay, well, let's pick 3 points, y'all. So let's not pick like 0, 0, 1, 0, 0, 0, and 2, 0, 0 or something. Let's pick 3 points. Throw in some negatives, throw in some numbers that are, I don't know if we want to go up to 2-digit numbers. You have to compute a cross product, which could be a little bit unpleasant, but so example. Somebody over here, give me Leo. 3, 4, 5. All right, that's reasonable. Somebody in this part of the class, give me another point. Yeah. I like the negative. 2, -5, 3. And somebody over here wants to give me a point. No. 184. Wow. An 8's in there. Let's do I don't know. Let me just throw a couple negative signs in here. -1, 8. -4. Okay. So this might take a little while, but I want you to do this maybe like, is it worth going to the boards? You just want to sit there and do it with your neighbors. Are we lazy? Okay. Turn to your side, introduce yourself to someone and try to work on it and pick, make the 2 vectors, make two vectors out of these 3 points, and then compute the cross product to find the normal vector. And see if you can write down the equation of the plane and maybe turn it into that ax plus by plus cz equals d form. And then once you have your equation, you should check that the other 2 points satisfy it. I mean, the point that you chose for x naught, y naught, z naught should satisfy it kind of trivially, but check that all your points satisfy it. So, but I would try to work with people around you and like maybe choose the same points to make the same vectors. Yeah, say hi, become friends.
Sounds good.
I'll stand here and drink coffee.
The other one that's not good on the other.
Everyone's on here. Guess I'll pause the recording. So not good. What is going? Wait. I gotta show you guys something. It's really random, but I want to see if you can see what I'm seeing here and try to figure out why it's happening. Sorry. Do you see? You see this? Doesn't it look like it's giving me the finger?
Yeah.
Well, where's that coming from? It's not. Oh, the microphone's in the way, hanging down. Oh, I was like, where's? I thought it was like a sun glare thing or something. Oh, it looks like it's giving me the finger. That's why. Okay, that was completely unnecessary for me to. All right. And then also, I just resumed the recording. So the recording paused with like these 3 points, and then it resumed with me talking about the screen giving me the finger. But okay, so like we found this equation, we did all the work and found the normal vector. found this equation, checked the points, and it all worked. That's awesome. But yeah, we should talk about some other like more basic equations. Because we first do tangent planes, we're going to use I mean, eventually I'm going to want us to almost always use this kind of form when we do tangent planes because it's just more general and nicer. But, and I'll start talking about tangent planes and partial derivatives and stuff on Friday. But it's good. I should prep with some general other equations. So other equations for a plane. Planes. Well, there are analogs of like slope intercept and point slope, right? Because we just did the analog of like that a times x minus x naught plus b times y minus y naught equals 0. And it's actually the same exact concept with normal vector and point and stuff. But so you could have something like slope intercept. I'm just making this up. Nobody calls it this. But you could have something like z equals mx plus ny plus b. Right? That's like, again, this is going to exclude vertical planes. But this is basically saying like m is called the x slope, the slope in the x direction. N is the y slope. And then b is the z-intercept, I guess. It's like, because the point 0, 0, b is on the plane that's on the z-axis. Because you need like two slopes to determine a plane. So now we're forgetting about vectors, going back to sort of more basic stuff, but like if this is the x direction and this is the y direction, like first off, I could raise it so it goes to the right z point. And then tilting it this way would give like the x slope, the slope in the x direction. And then tilting it this way would give the y, to the correct place would give the y slope. Does that make sense? That's another way you could sort of determine a plane is like z-intercept, get it to the right height, tilt it for whatever the x slope is in the positive x direction, tilt it whatever the y slope is in the positive y direction. Question? Well, the only way that would happen is if the plane was vertical, I think. Because otherwise, yeah, any x and y you should be able to solve for a z. Yeah, no, it's good. Like, right, it's not like, it's a little bit, we have more room in 3D, you're right, but planes at least kind of go 2 dimensions forever. So that's just kind of, and it's worth thinking about. This is something we're going to start doing, which is, this is actually going to be the analog with the derivative, which is like, one way to think, if you think about like a y equals constant cross section, that would be like putting a number in for y. And then you really just get z equals mx plus b, or it's a different b, but it's z equals mx plus constant. And so it really is a line of slope m. And that's in the x direction since y is constant. And then the same thing if you make x constant. So that's why it's like x slope is like the slope in the x direction. And then just the other one would be like, we have point slope form. So this would be like point slope form, which seems kind of silly, but you could also do a slightly more general version, which is like, I'm just trying to do the analogs with those equations for lines, which is if you do something like this, z minus z naught equals m times x minus x naught plus n times y minus y naught. And so m is still the x slope. Like it's the same m and n as before. And x naught, y naught, z naught is a point on the line. I mean, on the plane. Right, so now, because it goes, definitely if you plug in x naught, y naught, and z naught, this is satisfied because you get 0 on both sides. But Yeah. And actually, we'll talk about this. This is a nice equation too. And actually, it kind of does, I erased it now, but it kind of does look like if you move this point over, this expression over to the other side of the equation, subtracted it, it does look like the equation, the most general equation we had for the plane. And if you think about the ABC, like, just because we're out of time, I'll just say, like, if you compare this to like the A plus B times Y minus Y naught plus C times Z minus Z naught equals 0. If say C is non-zero, you could always scale it to be 1. Like I could divide through both sides by C or by negative C, I guess, because this, if I subtracted, I could get M times X minus X naught plus N times Y minus Y naught minus Z naught equals 0. And I'm just saying these look pretty much the same. But you need C to not be 0, which is equivalent to saying that the plane is not vertical. What does like this to this mean? It just means it's kind of like this, where it goes through this point X naught, Y naught, Z naught. So that tells you a point to have the plane pass through. And then the M tells you the slope in the X direction. And the N tells you the slope in the Y direction. But I'm just saying, like, it's not an accident that these start to look sort of the same. And because if C is 0, the vector is horizontal because it doesn't have a Z component. The normal vector is horizontal, ABC is horizontal. So that's a vertical plane. But if C is not 0, then the vector points something like this, so that it has slopes, X and Y slopes. I'll do more of this on Friday when we get into tangent planes and stuff, partial derivatives, but I just wanted to go ahead and say that. Okay, but we're out of time, so thank you. And I have office hours now and later, and I'm on email, and I'll post the Friday homework as soon as before lunch, hopefully.